Alright, so in this video I'm gonna be explaining another important article about domain adaptation, and the title of this paper is Interpretable Domain Adaptation for Hidden Subdomain Alignment in the Context of Pre-trained Source Models. So this paper in 2022. Domain adaptation aims to leverage source domain knowledge to predict target domain labels. Most domain adaptation methods tackle a single source, single target scenario, whereas source and target domain data can often be subdivided into data from different distributions in real-life applications, when the distribution of the collected data changes with time. However, such subdomains are rarely given and should be discovered automatically. And we call it domain discovery. I mean, there are some papers that first do domain discovery, for example, using mixture of Gaussians or let's say k-means, or a combination of k-means and mixture of Gaussian. And then once they get their sources, then they start domain adaptation. Okay, let's carry on. To this end, some recent domain adaptation works seek separation of hidden subdomains with respect to a known or fixed number of subdomains. Of course, for example, when you are working on a mixture of Gaussian, first you fix that you have, for example, k Gaussians. So it's mixture of k Gaussians. Then you continue. So k could be a hyperparameter. So let's carry on. In contrast, this paper introduces a new subdomain combination that leverages a variable number of subdomains. Precisely, we propose to use an inter-subdomain divergence maximization criterion to exploit hidden subdomains. Besides, our proposition stands in a target-to-source domain adaptation scenario where one exploits a pre-trained source model as a black box. Thus, the proposed method is model agnostic. By providing interpretability at two complementary levels, transformation and subdomain levels, our method can also be easily interpreted by practitioners with or without machine learning backgrounds. Experimental results over two fraud detection datasets demonstrate the efficiency of our method. So again, we denote the input space of predictive models as X, and we focus on binary classification prob, where we have two labels. In the pre-trained source domain, predictor gives the probability that example is classified as 1. In a target to source domain, H is given as a black box classifier of a wide variety of types. So in this paper, we generalize the method to a multi-subdomain setting for extending the flexibility of such domain adaptation approaches while preserving their appealing properties. We denote by X the feature space that encodes hidden subdomains. Note that features in X and X sub can be different. X stands for the discriminative attributes in predicting class labels, whereas X contains attributes that help discover hidden subdomains. So X sub T is target, X sub S is the source domain input, and P is just the distribution of your target, and X sub S is distribution of your source. But because each source has some subdomains, each source domain has some sub-source domains. Then, so we go over, we sum over ks, because we have, for example, ks subdomains in the source, and we have k sub t domains in the target. The similarly for a target, we can have subdomains. So, for example, k sub t domains for the target, and k sub s domains for the source. So very beautifully we can write the distributions. This is the modern machine learning, because we don't care, because in traditional machine learning we used to work on IID, which is a totally false assumption, and many of our problems in the generalization is just because of this simple thing that we always try to ignore. But now we are shifting the machine learning towards a new world, which is very adequate, very precise. Precisely, we are decomposing our source and target domains, so we know our distributions. We are not just saying that it's an IID. We are saying that we know which data point is from what subdomain and how it is mapped. So let's continue. So we define a set of examples of target and source domain respectively. So we assume there exists a mapping matrix S that relates hidden target subdomains to the source funds. So there is a map that maps, for example, this one to this one, maps this one to this one. So there is just a map that maps from target to source. We denote S sub ij, the scalar located at the ith row and the jth columns of S. And S sub I, S sub j represents the row and column vectors. So S sub ij takes the value 1 if the target subdomain is mapped to the source subdomain. So this is an S, we have a row and columns, and for example, this says that if it is 1, it means that this source subdomain is mapped to this target subdomain. So we can identify that. To enhance the interpretability, we encourage S to be sparse. Typically, we want one target hidden subdomain maps to only one source hidden subdomain. Well, that is very, very idealistic, but they encourage us to be sparse. And so we first provide details of our adaptation methods by starting with a known number of subdomains, and then generalize our method to handle a variable number of subdomains. So we have hidden subdomain adaptation with a known number of subdomains. Let's first assume that we face a domain adaptation problem for which we know a priori that the underlying number of target and source subdomains. So we formalize the target domain classifier like this. This is your target domain classifier. So H sub t is a predictor. This one is the predictor of the i's target subdomain. And M sub I is the probability. So M here is the probability that a target example belongs to this subdomain. Now, as our experiments involve both categorical and numerical features, the I subdomain density, this P, is thus computed by a product of densities of each dimension of X. We formalize the classifier of the I's target subdomain like this. And G is just a single domain adaptation that transforms data from the ICE target subdomain to the J source subdomain. We leveraged the work of Zhang in 2021 by setting this G, to be coordinate-wise domain adaptation functions. With known subdomains numbers K, the hidden subdomain adaptation consists of estimating the optimal subdomain separation and a relation matrix. Now we have estimation of X. Logically, separations of subdomains are significant if inter-subdomain discrepancies are large. As if subdomains were similar, they could be adapted using the same transformation, and there would be no need to distinguish them. Moreover, in a predictor weighting formalization, one benefits from a diversity between weighted elements. Here, such diversity is inherited from the differences between subdomains, as they likely spawn diverse transformations. So we search the optimal X by maximizing the inter-subdomain discrepancies. So this D is just a domain discrepancy measure. And here in this case, it's just a one-dimensional Wasserstein distance over each feature. Now, estimation of S in a weakly supervised setting. In this section, we stand in a case where a few target domain data are annotated. So once X is determined, one can minimize the prediction over a few labeled target domain points. So we get this S star. But L, this is the loss function. And we just leverage a softmax function. So in this approximation that we get S star, we have softmax for loss. Because remember, H is just a mapping to 0 and 1. It's a probability. The interval between 0 and 1 is the probability. So H is a probability, and then we can just cross entropy between them. It sounds logical. So hidden subdomain adaptation with a variable number of subdomains. So until now we know what we do, but we have what do we do when we have a variable number of subdomains? In such cases, a natural choice is to estimate the optimal couple K using weakly labeled target examples. So H, this one, is the estimated optimal target domain classifier of the previous section. However, when using a bagging strategy, we empirically observe that one can hardly find a single K substar that is significantly better than others. Indeed, the scarcity of D leads to high variability in bagging predictive performances. Therefore, instead of using H sub T with the optimal estimated K sub star as a target domain classifier, we propose aggregate multiple target predictors. So each H is obtained for different values of K. The weight associated with each possible subdomain number is handled by this matrix A, such that the target domain predictive models becomes this. And here sigma is just a softmax that encourages sparsity of weighting factor. So we can easily get our A. But for unsupervised hidden domain adaptation, because in real life application, the given pre-trained source domain predictive model is often well trained to be optimal one in the source domains. So when K is known, a necessary condition for X and S to be optimal one is this. When we have a variable number of subdomains, a necessary condition is 7. Basically, domain adaptation aims to align joint distributions of target and source domains. Thus, the alignment of the output distributions of classifiers is a necessary condition. In practice, X is fixed using equation 3, and one can search for S and A relying on such. So this is an estimation of S. The unsupervised optimization problem of S is this one. And again, W is just the 1D Wasserstein distance over the distribution of positive outputs. And empirically, we can write this Wasserstein distance as this sigma, summation over H sub t minus the inverse of the accumulation of a cumulative distribution function. But what if we have a temporal drift? So in this paper, we focus on practical case where the feature that encodes hidden subdomains is one temporal dimension, for example, time. Such a scenario is very common in real-life applications where data arrives as time goes on, like online learning. For example, in a payment fraud detection system, payment habits are different due to change of seasonality. Moreover, time is a 1D feature that can be efficiently subdivided. So we take into account the discrepancy between successive subdomains. And for the implementation, the proposed HSAV consists of 3 steps. We estimate separations of subdomains, then we estimate the corresponding sparse mapping factor S, then we combine predictions of variable number of subdomains relying on A. The rest of them is just details. So you can see the Kaggle fraud detection data set in the unsupervised. Here is the unsupervised setting. But here, instead of Kaggle fraud detection, we have real. This is real fraud detection. And here is the case of weakly supervised for real, again real, and here for Kaggle.